Hello students, welcome back to my channel JPPHYSICS. In last lecture, we have discussed about the important derivations from first and second chapter, that is rotational dynamics and mechanical properties of fluids. In this lecture, we are going to discuss about the derivations, important derivations from third and fourth chapter, that is Ktg and thermodynamics. Okay, so let's start our first derivation, that is pressure exerted by gas on the wall of the container. See, in this we have to consider, I will draw figure for this side. Okay, here we will consider one container which is in cube shape, cubical container, like this. Okay, this is x-axis, this is y-axis, and this is x-axis. Right one? Okay, so this is the gas container in which gas molecules are random in motion. Here the pressure is maintained so that the molecules are not going to collide with each other, but they will collide with the wall of the container. And that pressure exerted by that gas molecules on the wall of the container we have to find out. So we will consider this wall of the container, shaded wall. Okay, and here we are going to consider the pressure exerted by the gas molecule on this wall of the container. See, molecules are colliding or molecules are moving in all possible direction, x, y, z axis. But here initially we will consider for x axis only, in the direction of x axis. Then lastly we will generalize the equation. Okay, so if I consider Vx bar is the direction of that molecule which is going to collide on this wall of the container. What will happen? Say, there will be change in linear momentum of this gas molecule. Say, it will collide with the wall and get bounced back. Right one. If I consider this length and this breadth and height, say this is cube shape, therefore length, breadth, height will be same. So if I consider the length of this container as L, that molecule will cover the distance between two collisions. That is, it will start from this, collide with this wall, again this come back and collide with this wall. Means between these two collisions, it is going to cover the distance L plus L, that is 2L. Remember this thing in your mind? Okay. Now, what will be the change in momentum? Change in momentum of that one molecule. See, we are going to consider here average force applied by that one molecule. Average force applied by that one molecule on this wall of the container. There are number of molecules, they are colliding with all the walls, that is in x-axis, y-axis, z-axis. Correct? But here initially what we have considered only x-axis. Therefore, we have to consider the average force exerted by one molecule on this wall of the container. So, what will be that change in linear momentum? See, change in linear momentum. Change in linear momentum of molecule. Molecule. What will be that? What is the formula for linear momentum? Linear momentum having formula P is equal to mv. Right? Here we have considered the x direction. Therefore, this will be mvx. So, change in linear momentum, if we want to calculate, we have to consider final momentum minus initial momentum. That will give you the change in linear momentum. Why we are going to calculate the momentum? We know the second law of motion. What is second law of motion? Rate of change of momentum is directly proportional to applied force. And here we have to find out the average force applied by that one molecule on this wall of the container. Then how we can find out the force? That is change in momentum upon time. So we have to calculate here change in linear momentum of the molecule. So change in momentum will be mvx. See, this is final momentum. What is final momentum? This molecule collide with the wall and get bounced back. right one, and that time its direction is going to change. See here, we are not going to consider that y and z components because they are not going to alter, because their value is not, their direction is not going to be changed. Only the direction of that x-axis is going to change. Then that is, it is in positive direction initially, and when it get bounced back, direction will be negative. Right one, it collide with the wall, its direction get changed and it bounce back. But z and x-axis direction is not going to change. They are not going to alter. So we will consider only the component of this x-axis, right one. So initially that momentum is mvx, but when it get bounced back, its direction is get changed, or it is in opposite direction. Therefore that p final will be minus mvx. Right one, this is P initial, that is mvx. What will be P final? That will be minus mvx. So P final minus P initial means minus mvx minus mvx minus initial momentum. So what will be that? Minus 2mvx. 2mvx means this is the change in linear momentum. This is the change, minus 2mvx. See, means plus 2mvx. This much of a amount of momentum get imparted with this wall. Right one, if there is a change in momentum is minus 2mvx, means this much of momentum is given to this wall by the molecule. Right one, say you can prove like this also. Initial momentum is mvx. Right one, what is the change in momentum is minus 2mvx. Right, so mvx minus 2mvx, that will be the P final. What is that? Minus mvx. Mvx minus 2mvx. What I have told, that is plus 2mvx. This much momentum is imparted or is given to this wall. Means if it is given to the wall, I have to subtract that momentum. Right one. So mvx minus 2mvx, it will give you minus mvx. In this term also you can remember this. Okay, but when we are going to calculate this much momentum is imparted with the wall, so we will take only magnitude of this minus 2mvx. That is, we are going to calculate by the whole derivation. For the whole derivation, that is plus 2mvx. Okay, so here the change in momentum is nothing but the 2mvx. That is momentum minus 2mvx, and momentum imparted with the wall will be 2mvx. Okay, so what will be the average force? Average force applied or exerted by this molecule, single molecule, on that wall of the container, it is given by 2mvx divided by delta t. What is this delta t? Delta t is the time required for that collision. Means it collide with this wall, again come back and collide with this wall. Means between these two collisions, it required the time delta t. It required the time delta t. Then if I want to find out this time delta t, what I can write? See, velocity is nothing but the displacement upon time. Right one. So what will be time? Time will be distance upon velocity. Then what is the distance? Between two collisions, it has to cover L and L, that is 2L. It first collide with this wall, bounce back, and again collide with this wall. In between these two collisions, it covers the distance L plus L, that is 2L. Therefore, distance will be 2L. And what is the velocity? Velocity we know, it is 3x, right? So, after this, average force will be, average force is equal to, what will be that average force? See, 2mvx upon delta t. What is this value of delta t? That is this t is d upon v. This is delta t, 2L upon Vx. So I will write here 2L, and this Vx will get cross multiply. Therefore, here that will be Vx. So 2m Vx square upon 2L. 2 will get cancel. What will remain here? See, it will be m Vx square upon L. Right? This is the average force, that is mvx square upon L. But what we want? We want pressure. And what is the formula for pressure? We know that. What is the formula for pressure? Pressure is equal to force upon area. So if I put the value of force here, it will be mvx square upon L into A. This is the area. And what is area into length? It is volume. See, what will be area of this cube? Length into length, side into side, that is side square. Means L into L into L. This A is L square. This L square into L will be L cube. And what is L cube? It is nothing but the volume. So, this will be mvx square upon volume. Right? Here Vx is there, therefore I am not going to write V because it will look like same. So I have written here volume. Okay, this is the average pressure. Right one. If we have taken that average force, therefore pressure will be also average pressure exerted by the molecule on that wall of container. One molecule. But here there is not one molecule. There are n number of molecules. So this total pressure, total average pressure exerted by one molecule can be written as m upon volume, and in bracket it will be Vx1 square plus Vx2 square plus Vx3 square, Vx2, Vx3 square, and so on. Are you getting this? See, this is only for one molecule. But there are number of molecules. So we have to add all that average pressures. Right one. So P average is equal to, this mass is as it is, volume is as it is. But in place of Vx, we have to take all that velocities. See, this m is the mass of each and every molecule. Therefore, that will be mvx1 square upon volume, mvx2 square upon volume. That mass upon volume is constant. So, take it out, and only the remaining term will be Vx1 square plus Vx2 square, Vx3 square, and so on. Now, if I consider, see, here, average of this, if I consider Vx square average, how I can write this Vx square average? Average of this square velocity. Average of this square velocity. At that time, I have to add all that velocities and divided by total number of molecules. Here one assumption is there, that is small n is nothing but the number of molecules per unit volume. Number of molecules per unit volume. Per unit volume. N is the number of molecule per unit volume. So what will be the total number of molecules? That total number of molecules will be N into V, that is volume. We have to take the assumption like this. That is, consider a container which contains gas, it having the n number of molecules per unit volume. Let Vx be the velocity of the molecule along x direction. All these things you are going to write initially. And then you have to draw this diagram, show this direction and shaded wall, and you are going to write all this derivation. So, if I consider average of this square velocity, what I can write for n number of molecules? I can write Vx1 square plus Vx2 square and so on divided by capital M. That is total number of molecules present in that container. So what will be value of this Vx1 square plus Vx2 square and so on? That will be n into Vx square bar. Always remember, first you have to write square and then this bar sign. Average of what? Average of square velocity, not the square of average velocity. Are you getting this? It is a average of square velocity, not the square of. Don't write like this. Okay, always write like this. Okay, average of square velocity. So that value of Vx1 square plus Vx2 square, that will be nVx square bar. So I can put that value in this equation. That equation will becomes, see, this equation will becomes pressure average. Average pressure is equal to mass upon volume as it is. Right, and in bracket this term, at this term I will write nVx square bar. nVx square bar, that is average of square velocity. Now this is only for x-axis, but we have to consider all the axes. So here if I take square of average velocity, only this is in x direction, but I am taking all the direction in this. So what I can write? I can write Vx square bar plus Vy square bar plus Vz square bar. Yes, x, y and z axis if I consider, resultant of that all vectors will be V bar, V square bar. So if Vx, Vy, Vz are same, see, velocity of molecules in x, y direction will be same. Average velocity we have considered. So these all the velocities will be same. So in place of Vy square, Vz square, we will take Vx square. If Vx square bar is equal to Vy square bar is equal to Vz square bar, then in place of this Vy, Vz square bar, I can write Vx square bar. So what will this equation becomes? See, V square bar is equal to 3 Vx square bar, right? See, Vx, that will be 3 Vx square bar. In place of y and z, you are going to write Vx only. So V square bar will be Vx square, Vy square and Vz square bar will be 3 Vx square bar. Why I have taken like this? See, we have to put the value of this Vx in terms of V square only. So what will be the value of Vx square bar? That will be 3 will going to divide here. So V square bar upon 3. Right? This value Vx square bar will be V square bar upon 3. So put this value in this equation. You will get P average is equal to mass into total number of molecules. In place of this, you are going to write V square bar divided by 3 and this volume as it is. Means this formula will be 1 by 3 mNV square bar upon volume. This is the required formula for pressure exerted by the gas on the wall of the container. Many students ask me how this derivation can be done. They feeling difficult to derive this expression. But actually, this derivation is not difficult. But some things you have to remember that initially only we consider x-axis. So change in momentum along that x-axis we have taken. This much of plus 2 mvx momentum is imparted with that wall of the container. So we have taken here plus 2 mvx. We have find out the average force exerted by one molecule on this shaded wall of the container. Therefore, it is 2 mvx by delta t. Rate of change of momentum is nothing but the force. Therefore, change in momentum upon time. We know velocity is equal to displacement, distance upon time or displacement upon time. Therefore, t is equal to, if I take this t, here, then T is equal to D by V. But what is the distance covered by the molecule in two successive collisions? What is that distance? It is L plus L, right one, that will be 2L upon Vx. That time, value of time we are going to put in this equation, that is average pressure will be, average force will be 2mvx upon delta T. What is delta T here? Delta T is 2L upon Vx. If you are not going to understand, you can take like this also. Delta T is equal to, okay, D upon V. Therefore, 2mvx upon 2L upon Vx. Vx will get cross multiply. Therefore, Vx will be here. So, what will be the final formula? mvx square upon L. Now, average force is not required. Average pressure is required. Therefore, average pressure will be average force upon area. So, what is force? mvx square by L and upon area. But what is length into area? It is nothing but volume. Therefore, P average is equal to mvx square upon volume. Right? Now, P average, mass upon volume, it is constant. It is for one molecule only. But we have to consider n number of molecules. So, we have taken Vx1 square plus Vx2 square and Vx3 square, so on. Now, what will be the average square velocity? See, Vx square bar is equal to Vx1 square, Vx2 square divided by total number of molecules. This is for only one molecule, second molecule, third molecule. What will be the total number of molecules? Average velocity. What we want? Average average of square velocity. Therefore, make the summation of all the square velocities divided by number of molecules. Therefore, divided by n. Then what I will get? The value of Vx square average, means this value into this total number of molecules will nothing but sum of all these square velocities. Therefore, Vx1 square plus Vx2 square will be n into Vx square bar. Average velocity get multiplied by total number of molecules. That's why we get the sum of all the square velocities. So, if I put the value in P average, I will get P average is equal to mass upon volume into n into Vx square bar. But it is for only x-axis. But we know that molecules are colliding with all the walls of the container, that is along x-axis, y-axis and z-axis. Therefore, we have to consider that three axis. Therefore, I have written V square bar is equal to Vx square, Vy square and Z square bar. Summation of all these vectors. Therefore, if we put that Vx in place of Vy, Vz, because these velocities will be same. If I put that value in place of y and z also, we will get expression like V square bar is equal to 3Vx square bar. Then what will be the value of Vx square bar? See, we have to put up here the value of Vx square bar. Therefore, Vx square bar will be V square bar upon 3. V square bar, Vx square bar is equal to V square bar upon 3. Put this value in this expression and finally we get the average pressure exerted by the gas on the wall of the container as 1 by 3 mass into number of molecules, total number of molecules, average square velocity divided by volume, that is 1 by 3 mnv square bar upon volume. Remember one thing, don't write like this. See, Vx bar square. No, it is Vx square bar. Okay, you understood this expression? If you want, you can take a screenshot of this derivation. Okay, now, next derivation we are going to do, that is Mayer's relation. That is Cp minus Cv is equal to R. Right? This expression, see, this derivation can be asked for 3 marks. Right? Now, next derivation, that is Mayer's relation. Cp minus Cv is equal to R. This relation also can be asked for 3 marks. Okay. Let us do that derivation. Okay. Cp minus Cv is equal to R. This derivation we have to do. What is CpCv here? Molar specific heat at constant pressure minus molar specific heat at constant volume equal to constant R, that is universal gas constant. We have to prove this relation. This relation is called as Mayer's relation or Mayer's equation. We have to derive the expression for that derivation, that is Mayer's relation. What we have to consider here first, see, what is Cp and Cv? That is molar specific heat at constant pressure, molar specific heat at constant volume. Means when the pressure is constant, the heat supplied is equal to what will be the formula? That formula we have to consider first here. What I am saying, if we are heating the gas at constant pressure, that time what will be the formula for that heat? And if that heat is given to the gas at constant volume, what will be the formula for that? We are going to consider first. So let us consider Q1 be the heat given to the gas at constant volume. At constant volume. Then what will be the formula? See, I can write Q1 is equal to Cv dt. If we consider 1 mole of gas, that time N will be equal to 1, right? So what I can write the formula? Q1 is equal to Cv into dt. See, in 10th standard also you have seen, in 11th also you have seen that Q is equal to Ms into delta T. There are two formulas for Q, that is Q is equal to ml and Q is equal to ms into delta T. Here when the temperature increases, that time you are going to take the formula Q is equal to ms into delta T. And when the state gets changed, that time you are going to use the formula Q is equal to ml, where L is the latent heat of fusion or vaporization and all that. So here only temperature goes on increasing. Right one. So that time we have to use the formula Q is equal to ms into delta T. But this is principal specific heat and we have to consider molar specific heat. Then what is the relation between them? C is equal to m into S. Right. So that I have written this as like, see, Q1 is equal to Cv into delta T. Right one. And why I have not taken this N? Because we are going to consider 1 mole of gas here. Means initially you are going to write like this. Let us consider 1 mole of gas heated by supplying the heat Q1 at constant volume. So we can write Q1 is equal to Cv into delta T. This is change in temperature. This is molar specific heat at constant volume. Means this Q1 is nothing but Cv into delta T. Right one. Now, if this is at constant volume, what will be the, see, if here only the increase in temperature, it is change in internal energy, right one? So you can write it like this is equal to du. This is change in internal energy only. There is no any work done takes place because this process is happening at constant volume, and as volume is constant, there will be no any work done. Right one. Only increase in temperature means only change in internal energy. So Q1 is nothing but Cv dt can be equated to change in internal energy. For 1 mole of gas we are going to consider. Therefore, there is no any N here. Okay. Now, Q2 be the heat supplied to the gas at constant volume. Q2 be the heat given to gas. You can write given to 1 mole of gas also at constant pressure. At constant pressure, then Q2 is equal to Cp into dt. Q2 is what? Cp into dt. But what will be the actual formula? See, this is Cp into dt, right one. But when we are providing the heat at constant pressure, that time this heat is nothing but used for two things, right one, to increase the internal energy and to do some work. Are you remember this? At constant pressure, when you are going to consider the process, at that time there will be change in internal energy and also some work will get done. Therefore, this du plus dw will be equal to Cp into dt. Means this heat supplied will be used for two things. One, to change in internal energy, and another to do some work. Right one. So, here Cp into dt is equal to du plus dw. Therefore, I can write Cp into dt. What is du here? If I take this equation number 1 and equation number 2, if I put 1 into, what I will get? Cp into dt is equal to Cv dt plus dw. Right? dw. What is this work done here? Work done is nothing but pressure into change in volume, P dV. We know this formula. What is dw? dw is nothing but pressure in change in volume. I want to put this value of change in volume. For that, I will take ideal gas equation. What is that ideal gas equation? If I consider that ideal gas equation for 1 mole only, that equation can be written as PV is equal to RT, right? We know this. Actually, PV is equal to nRT. But if 1 mole of gas is there, we can consider PV is equal to RT only. Therefore, if I differentiate this, see, P into dV is equal to R into, see, PV is equal to RT actually, and then P into dV is equal to R into dt. What is equation? PV is equal to RT. If I written here P into dV, change in volume, work done. Pressure is constant here, right? So P into dV is equal to R into dt. Means what is the value of P dV? It is R into dt. So this equation will becomes like, see, Cp into dt is equal to Cv into dt plus, in place of dw, we are going to write Pdv. And what is the value of Pdv? It is R into dt. So put here R into dt. Are you getting this? See, we have taken Q2 as a heat supplied at constant pressure, and we know that at constant pressure, heat is used for, given heat or supplied heat is used for two things. One, to increase the internal energy or to increase the temperature of the gas, and some amount of heat is used to do some work. Right one. So, Cp which is Q2, value of Q2, can be written as Cv dt plus dw. But what is work done? What is the formula for work done? It is P into dV. Small amount of change in volume is there. Small amount of work we have taken. So dV is equal, dW is equal to P into dV. But I want to put this value of dV in terms of dt, so that I have considered ideal gas equation. PV is equal to RT. Therefore, we can write P into dV. See, this P is constant. Therefore, P into dV is equal to R into dt. So, put that value of P dV in this expression in place of dW, that is R into dt. So, dt will get cancelled. So, what will remains here? Cp minus Cv is equal to R. This is the required relation, which is called as Mayer's equation or Mayer's relation. You got this? You will get 3 marks for that. But initially you have to write all that things. Let us consider 1 mole of a gas. It is heated. If it is heated at constant volume, Q1 can be written as Q1 is equal to CV into dt. But when we consider at constant volume, there will be only the change in internal energy. Therefore, Q1 is equal to CV dt is equal to du. That is change in internal energy. Here no work is going to be done because there is no change in volume, right? So let equation number 1, N is 1 here, therefore 1 mole of gas, therefore only the equation will be Q1 is equal to CV dt. Now if Q2 be the heat given to the gas at constant pressure, then that Q2 is nothing but Cp dt because it is at constant pressure. Therefore, Cp into dt that can be given as du plus dw. Here at constant pressure, the heat supplied is used for two things: to increase the internal energy and to do some work. Therefore, formula will be du plus dw. Let's put that value of du from equation number 1, and in place of dw that will be pdv. But to put this value of pdv, we have to consider the ideal gas equation, that is pv is equal to RT. Therefore, pdv is equal to RDT. Why I have written P as it is? Because we are going to consider Q2 is at constant pressure. Therefore, pdv is equal to R into dt. In place of pdv, write that RDT. Therefore, equation will becomes Cp dt. See here, Cp dt is equal to Cv dt, and in place of pdv, that will be RDT. Therefore, Cp dt will get cancelled, and the last relation will be Cp minus Cv is equal to R. This is nothing but the Maer's relation. That is, also they can ask the question, derive the relation between Cp and Cv, or they can ask the question, prove that Cp minus Cv is equal to R, or also they can ask the question, derive the expression for Maer's relation. Okay, for all these questions, answer will be the same. You will get 3 marks for this answer. If you want to take the screenshot, take it. Okay, so this is the second derivation. Now we are going through the derivation from thermodynamics. See, in Ktg, there are another derivations are also there. That is Kirchhoff's law and Stephen's law, but that derivations are very small. They can ask for 2 marks only. So I have taken only these 2 relations or 2 expressions, that is expression for pressure and another, that is Cp minus Cv is equal to R. Then we are going to do the third derivation from thermodynamics, that is work done in isothermal process. Work done in isothermal process. Okay. So first you have to know what is mean by isothermal process, right? We are going to do the expression for work done in isothermal process. What is isothermal process? First you have to consider. What is isothermal process? The process which takes place at constant temperature. Isothermal means temperature is constant here, and at that constant temperature the process happening is called as a isothermal process, and we have to derive the expression for work done in case of isothermal process. So let us do that expression. First here we have to consider, that is gas is processed at constant temperature, means at that time what we can consider? We can consider Boyle's law. Why? Because what Boyle's law having the statement, that is pressure is inversely proportional to volume at constant temperature, and here we have to consider constant temperature. Then what is the Boyle's law? According to Boyle's law, PV is equal to constant, right? Means what? P1 V1 is equal to P2 V2 is equal to constant, right one? And now we have to find out the work done in case of isothermal process. We know the formula for work done. What is that formula for work done? That is P into dV. Pressure into change in volume. This is the formula for work done, and we have to find out that work done only. So what is dW? dW will be P into dV. Right? If I want to find out whole work done, total work done, process, total work done takes place in whole process, then I have to integrate this. Therefore, W is equal to integration of dW from what to what? Initial volume to final volume. See, if there is a one container and piston is there, and this gas is heated at constant temperature, means temperature is not going to be changed, means this volume is going to be increased. Right one means from initial piston position it goes to this position, means its volume get change. Right one, through this quantity, means there is a change in volume. Then what is the formula? Initial volume if it is VI and final volume if it is VF, then what will be the change in volume? That will be VF minus VI. Means volume is taking change from VI to VF, and here we have to consider that only. So this work done is taking place in increasing the volume of that gas from V initial to V final. Means here the volume of the gas is going to be increased, and if there is a change in volume, there will be work, and that work is nothing but P into dV. But from what value to what volume is going to be changed? That is V initial to V final. Now we have to put the value of pressure here from this expression. PV is equal to constant, or we can take that ideal gas equation, PV is equal to nRT. Right one. Then what will be the value of this P here? nRT upon V. Correct? What we get the value? P is equal to nRT upon V. This is nothing but the ideal gas equation. If I put this pressure in this equation, what I will get? W is equal to integration of P. In place of P, I will write nRT upon V into dV from V initial to V final. Okay, work is going to do for increase in volume from V initial to V final. Now this nRT is constant, so take it out. W is equal to nRT integration from V initial to V final of that dV upon V. And you know what is the integration of 1 upon x? It is log of x. Right? So here there is a 1 upon V dV. What will be the integration of this? That will be log of V from VI to VF. Put that limits, what we get? nRT in bracket log of V final minus log of V initial. And when there is a subtraction of log, we take the division, right? So nRT log of V final upon V initial. See, the students which are from B group, they are not going to understand these terms which are related to integration. So you have to remember this. In second chapter of 11th, you have studied all the integrations and derivations which are required for physics. Right? Basic integration and derivation part is there. From that only, this is one standard integration. That is integration of 1 upon x dx. It is nothing but log of x. And here if you observe, it is dv upon v. Means what? It is 1 upon v into dv. Right one? dv upon v means what? 1 upon v into dv. 1 upon x into dx, that is log of x. Therefore, I have taken here log of v. And when we put the limit, we have to subtract the lower limit from upper one. Therefore, in place of V, you have to write first Vf and then Vi. Therefore, log of Vf minus log of Vi. And then another law is there, that is, or rule is there, log of A minus log of B can be written as log of A upon B. If there is a subtraction of log, you can take division of log. Subtraction of log, you can take log of division. Log of division, that is A upon B. Therefore, I have written here Vf upon Vi. These steps get forgot by the B group students. That's why I have repeated this part. See, nRT log of Vf upon Vi. But this is log to the base E. And if I want to change this to the base E to the base 10, then I can write W is equal to 2.303. When you want to change this to the base E to the base 10, we have to multiply the term by 2.303. It is the constant factor you have studied in chemistry also. Right one? 2.303 nRT log to the base 10. Right one? Vf upon Vi. So this is the work done in isothermal process. This is the expression for work done in case of isothermal process. That is 2.303 nRT log of Vf upon Vi to the base 10. What we have done, we have considered Boyle's law, that is PV is equal to constant, that is P1 V1 is equal to P2 V2 is equal to constant. But here we have to consider the work done. Why work done? See, volume is going to be changed, and whenever there is a change in volume, there is a work done. So that work done can be written as dW is equal to P into dV. So I have to put the value of P here. And here the volume is changing in between Vi and Vf. Therefore, I have to take the integration of this dW from Vi to Vf. But here, what is the value of P from ideal gas equation? That is PV is equal to nRT. P is equal to nRT upon V. This V is multiplied here, it will get divided. Therefore, nRT upon V. Put this value of P in this expression. What we get? W is equal to integration of nRT upon V dV from Vi to Vf. Then again, nRT is constant. Take it out from the integration sign, and integration of 1 upon V dV will be log of V. Then all that part will be there. So the last expression, which comes as 2.303 nRT log of Vf upon Vi to the base 10. This is the expression for work done in case of isothermal process. This question can be asked for 3 marks, okay, in your question paper. So if you want, there is no any need to draw this diagram. Only for understanding, I have drawn this. This is also for you, that is laws which we have used here, formulas which we have used in this expression. So if you want, take the screenshot. Okay. So next derivation or last derivation of this lecture, that is work done in adiabatic process. Okay, let us do that. Work done in adiabatic process. See, in adiabatic process, there is a no any term constant, means there is a no any exchange of heat takes place in the gas. Okay, so work done in adiabatic process. Adiabatic process. Okay, so here we have to consider the expression for adiabatic process. What is that expression for adiabatic process? That is PV raised to gamma is equal to constant, where gamma is nothing but Cp upon Cv. As here no terms remains constant because there is no any exchange of heat. In isothermal process there is exchange of heat and therefore temperature remains constant. But here not the case. Therefore, we have to consider the equation as PV raised to gamma is equal to constant. In that, we have considered PV is equal to constant in isothermal process. Here, we will consider PV raised to gamma is equal to constant. I will take this constant as C. Okay. Now, we have to find out work done here. So, formula will be same, that is work done will be P into dV. Right one. Now here we are going to put this value of P from this equation, that is PV raised to gamma is equal to constant. What will be that value of P here? See, I will write again that formula. PV raised to gamma is equal to constant C. Then what will be the value of P here? C upon V raised to gamma. Right? So put this value of P in this expression and take the integration from initial volume to final volume. Okay. So what will be the work done? Work done will be, process is same. We are going to consider initial volume as VI, final volume as a VF. This formula can be written as C, like this also. P1 V1 raised to gamma is equal to P2 V2 raised to gamma is equal to constant. Right one. Volume pressure, both are going to be changed. Right one. So P1 V1 raised to gamma is equal to P2 V2 raised to gamma is equal to constant. So here, what is the work done? That is dW is equal to integration of dW, that is integration of P dV from V initial to V final. If I put the value of P here, then it will be C upon V raised to gamma into dV from initial volume VI to final volume VF. Here constant term is C, therefore take it out and the term will remain 1 upon V raised to gamma into dV initial to final. So don't write now log of V raised to gamma. No, because gamma is Cp upon Cv here. Right one. So here we have to take this V raised to gamma in numerator. That in isothermal only 1 upon V dV was there. Therefore it is 1 upon X, like that. Therefore log of V will be there. But here V raised to gamma is there. So we can't take 1 upon V log of V integration here. So we have to do this integration in another way, like this. See, V raised to minus gamma into dV. Why minus gamma? See, numerator. This term from denominator will come to the numerator. Power will get changed. Plus, it will become minus. So, from Vi to V final. Then what will be the integration? See, as it is Vi to Vf. V raised to minus gamma plus 1 divided by minus gamma plus 1. Again, I give this formula for you. See, x raised to n dx. What will be the integration of this term? This will be x raised to n plus 1 upon n plus 1. Right? Power plus 1 divided by that increased power. Right one? X raised to n plus 1 divided by n plus 1. Similar to that, V raised to minus gamma plus 1 divided by minus gamma plus 1. Right one? You got this? This is the integration. Oh, we have written the integration. So, no, we have to put the limit now. What will be the limit? V initial to V final. We have taken that integration. So, not integration sign will be there. V raised to minus gamma, having the integration V raised to minus gamma plus 1, and that power will be again in the denominator, that is minus gamma plus 1. Can I write like this? See, C upon this minus gamma plus 1, I will write 1 minus gamma. No any change is there, because here the sign is minus. I will write there and 1 will be here, that is 1 minus gamma, and this will be as it is. That is V raised to minus gamma plus 1 from V initial to V final. Now we have to put the limit, upper and lower limit here. In place of V, initially I will write Vf, and minus in place of V, that will be V initial. So what will be term C? W is equal to C upon 1 minus gamma as it is, and in bracket it will be Vf upper limit raised to minus gamma plus 1 minus initial. In place of V you have to write V initial. Therefore V initial minus gamma plus 1. Now what is this C? C is nothing but the constant, and it having value P1 V1 raised to gamma, P2 V2 raised to gamma. All these quantities are same. P1 V1 raised to gamma is equal to P2 V2 raised to gamma. Means if I consider P initial V initial, what I can write? See, P initial V initial raised to gamma is equal to P final V final raised to gamma. Means constant having both these values. So what I am going to do here, if I take this C inside the bracket, where there is a Vf, I will write the term Pf Vf raised to gamma, and when there is a Vi, that is V initial, I will take the value of constant C as P initial V initial raised to gamma. Are you getting this? Where the value is V final, you have to take this value, that is P F Vf raised to gamma, and when there is a V initial, then you have to take the value P initial V initial raised to gamma, because all this is equal to constant C. P V1 raised to gamma, P2 V2 raised to gamma is equal to constant. See, so I will take this C like this. W is equal to 1 upon 1 minus gamma. In this, if I multiply this Vf by this C, I am going to multiply by Pf Vf into this P Vf raised to minus gamma plus 1. See, you got this? See, I have taken inside the bracket, but how? If there is a V final, I have taken the term P final V final raised to gamma, value of C like this, minus. Here that value will get changed like this, P initial, V initial and V initial raised to minus gamma plus 1. Here there is a raised to gamma. Okay. Now Vf raised to gamma, Vf raised to minus gamma plus 1. If I add this, whenever there is a multiplication, there is a addition of power. You know this rule of indices. A raised to m into A raised to n is equal to A raised to m plus n. Right one. Here Vf raised to gamma into Vf raised to minus gamma plus 1 means there will be addition of power, that is plus gamma minus gamma plus 1. This plus gamma and minus gamma will get cancel, and only the term remain will be Vf raised to 1. Therefore, W is equal to 1 upon 1 minus gamma in bracket. This Vf raised to gamma and this Vf raised to minus gamma will get cancelled, and remaining term will be Pf Vf only. Because raised to gamma, see, I will do here V raised to f plus gamma minus gamma plus 1. Right one, this gamma will cancel, only the remaining term will be plus 1, that is Vf raised to 1, simply Vf. Minus, here will be the same thing, V raised to gamma, Vi raised to gamma, Vi raised to minus gamma, plus gamma minus gamma will get cancelled, and remaining term will be P initial, V initial. Okay, so this is the formula for work done in case of adiabatic process, that is 1 upon 1 minus gamma in bracket Pf Vf minus Pi Vi. This is the required expression for work done in case of adiabatic process. This derivation is somehow bigger, but the terms, if you step by step, if you remember, if you try to remember that things, that will be easy. write that derivation for 1 or 2 times, you can able to write the derivation without saying. Are you getting this? First, try it for or write it for 1 or 2 times, maybe for 3 times. You will get practice and you can, but try to understand each and every step. Don't make the tuffication. See, try to understand each and every step and then try to write the derivation. Okay. I have given you all the information of each and every step. Here there is an adiabatic process, therefore we have to consider the equation PV raised to gamma is equal to constant. And here gamma is nothing but Cp upon Cv. You have to write initially, let us consider 1 mole of a gas, and here we are processing the gas adiabatically. We are going to consider the adiabatic process. In case of adiabatic process, we have to consider the gas equation like PV raised to gamma is equal to constant. Here P1 V1 raised to gamma is equal to P2 V2 raised to gamma as constant. Therefore, work done is nothing but dW is equal to P into dV. Then put the value of this P from this equation, that is PV raised to gamma is equal to C, then P is equal to C upon V raised to gamma. Put this value of P in this equation, you will get integration of C upon V raised to gamma dV from initial volume to final volume. And then if you consider the derivation, W is equal to C will be constant, come out of the integration sign, and 1 upon V raised to gamma dV derivation, you have to use the formula or you have to use the rule that x raised to n dx, integration of this term will be x raised to n plus 1 upon n plus 1. The power is going to be add by 1 and that power you have to take in denominator. Therefore, here there is a v raised to minus gamma. Here it is in denominator. When it comes into numerator, it will be minus 1. Minus gamma. Why I am explaining this? Because B group students feel much more difficulty in these terms or in these steps. Therefore, I am again and again explaining. Right? See, when it is in a denominator, it having power plus gamma. It will become minus gamma when it come in numerator. Therefore, v raised to minus gamma into dv. But here the term like x raised to n into dx, like this. We have to add 1 in the power and that power will be also in the denominator. This is the rule of integration. So, v raised to minus gamma plus 1 and this minus gamma plus 1 again in the denominator. Now, this minus gamma plus 1 can be written as 1 minus gamma, right? So, I have taken it outside because it is constant term. Therefore, C upon 1 minus gamma, and then you have to put up the upper and lower limit neatly. Why I am saying that? Because these notations are very important. In place of VF, in place of that term, no, when we are going to multiply this VF raised to minus gamma plus 1 by this C, we are going to put the value of C as PF VF raised to gamma is equal to constant. That is final volume, final pressure. Okay, and here there will be initial volume, initial pressure. Value of C will be P initial, V initial raised to gamma. So if you put that value, you will get the expression at last as W is equal to 1 upon 1 minus gamma P final V final minus P initial V initial. This is the derivation for work done in case of adiabatic process. You got these derivations? If you have any doubt regarding these derivations and also that small derivations from these chapters, you can ask me in comment box. I will try to answer that questions. If any another doubt means from that derivations also, you can ask me in comment box. I will give the answer for that. And please comment me in the comment box. If you like the lecture, if any query in the lecture, I will improve that. Okay. So, if you like these lectures, like my channel, share and subscribe it, and also press the bell icon so that you will get notification for next lectures, because in next lectures I am going to derive the expression from next 2 chapters. Okay, so for today, thank you.